Okay, I wanted to make a quick video on the Schmidt process. Okay, suppose that you've got a linearly independent set of vectors in Rn, so I've got u1 through un. Okay, if they are actually in Rn, you could see that because they're linearly independent in this case, this would actually be a basis for Rn. But this generalizes, they don't necessarily have to be a basis. You could have this in maybe fewer vectors in Rn, and this will still end up working here. Okay, here's it was. So you've got this linearly independent set. Okay, we're going to create a new set of vectors in Rn which has exactly the same span as this original set, but the vectors here are going to be orthogonal. Okay, and a process for doing that is something called the Schmidt process. I posted a previous video that had a little of the geometry in 3 space associated with this process. Okay, let's go ahead and see how you get the set of V's from the set of U's. Okay, V1 is actually the original U1 vector, so no change there. V2 is U2 minus the projection onto V1 of U2. Okay, it turns out if you take the dot product of these with the projection definition here, you will get 0. Okay, alrighty, so this is how this works here. Okay, your book has a slightly different way of writing it. I wrote it in terms of projections here. Okay, the third vector, V3, is U3 minus the projection of the U3 vector on V1 and V2. Okay, so you can't just jump into this process. You have to compute the previous ones to get the next one. Okay, all right, and then you continue this process all the way to the end. So the very last one is u sub n minus the summation I goes from 1 to n minus 1 of the projection of the u sub n vector on each of the previous ones. And this ends up giving you an orthogonal set, okay, with the same span as the original vectors. If you want these to be orthonormal instead of just orthogonal, of course, just like any case, you could just take the orthogonal vectors and normalize them, that is, divide by their own magnitudes in each case, and you will have an orthonormal set. Okay, I'm not going to go through the proof of this thing, but the proof is basically by induction. Okay, alrighty, let's take a quick example here. I've got 3 vectors here, 1, 1, 1, 2, 0, negative 1, 0, 1, 1. Okay. All right, these are linearly independent, though I have not shown that. Okay, we'll just assume they are. You might consider what would happen if you use this Schmidt process on vectors that are not linearly independent. In other words, linearly dependent. Give that a little thought here. But let's go through the process here. So V1 is just the same as U1, nothing to do there, so that's 1, 1, 1. Okay, V2 is our second vector in the original, so that's U2. 2, 0, negative 1, minus the projection of the U2 vector on V1 here. Okay, so if I take the dot product of these 2 vectors here, okay, I would get 1, so that goes in my numerator. I'm getting the scalar projection here first. And then what? Times or over what? The dot product of V1 with itself. You can see that that would actually end up being 3. Don't forget to multiply by the vector v1. So there's, whoops, there should be a subscript 1 right there. Okay. Alrighty, so there we've got the vector 1 there, and there you go. So you actually perform the arithmetic on this, okay? And I ended up with 5/3, negative 1/3, negative 4/3. You can see, factor out the 1/3. It would be 1/3 times what? 5, negative 1, 4. You might take the dot product of these 2 vectors just as a check here and see that you indeed get a dot product of 0. Okay? Now, let me explain here in this process. I went through the process. See this ugly 1/3 here? I could actually get rid of that 1/3 and have my V2 be the vector 5, negative 1, negative 4 if I actually wanted to. You have to go through the entire calculation, and then I could either normalize this vector if I wanted these to be normal right now, or I could get rid of that 1/3 and it's not going to matter. I really wish I had. The calculation would be easier. Okay, but you have to get through the calculation before you can cast out any scalars. Okay. Alrighty, I just retained it, so I'm doing this very mechanically. Okay, what's V3? Okay, so that is what? U3 minus what? The projection of U3 on V1, and on, you want to subtract the projection of the U3 vector on V2 also. So that's going to be minus, okay, let's get the scalar projection. The dot product of these two is 2, that goes in the numerator. The magnitude of V1 is actually square root of 3, so that's squared on the bottom. In other words, V1 dotted with V1, so that's minus 2/3, 111, minus, okay. Okay, here's where I was saying I actually retain the 1/3 here, but I take the dot product of this with 0, 1, 1, and I got negative 5/3. The magnitude of this vector here ends up being the square root of 49 over 9, or square root of 42 over 9, or the dot product with itself, if you wish, is 42 over 9, okay, times the original. Okay, you've actually got to do the ugly arithmetic here. Actually, see, in this case, I could avoid the fractions had I just used 5, negative 1, 4 here. 5, negative 1, 4, and the arithmetic would be slightly easier. Try to avoid fractional arithmetic as much as possible, but I'm doing it mechanically here. Anyways, what you get is negative 1/14, 3/14, negative 2/14, or a 7th there, but I factored out a 14th here, so I went negative 1, 3, and negative 2, okay? So these are my three vectors. That's V1, V2, V3. These are what? Orthogonal. If I take the dot product of any two, which is something you might check, I get what? 0. Okay? Now, any scalar multiples of these would do. So once again, notice I've circled 1/14 out here. I could actually cast that out. And I did that here just as a restatement. 1, 1, 1, 5, negative 1, 4. Negative 1, 3, negative 2 is orthogonal. It's much easier to check the orthogonality in this case. Dot product here would be what? 5 minus 1. This is supposed to be a minus 4. Okay. Dot product here would be what? 0. Okay, the dot product over here would be negative 1, 3, negative 2, 0. Okay, dot product here, negative 5, negative 3, and positive 8 makes 0. Okay. Here I also did what? Took these vectors and did what? Normalize them. This would be what? A set of orthonormal vectors that span this original set of 3. Okay, so this would generate a subspace, okay, or actually that would generate all of our cube. This would generate exactly the same set, or the same space. Okay? Anyway, so this is the idea in these. Okay? So the calculations can be arduous sometimes, but they should be more or less straightforward. I just like to remember it this way. But again, if you want to write out what the projection is in terms of dot products, that's a good way to do it too. Okay? All right. Well, I hope you understood this and you can do all those problems that I've assigned now.